We know that some parameters, like the weights and bias of a linear regression model, can be optimized directly by adjusting them using gradient descent. But there are some parameters which it doesn't make sense to optimize directly. For example, let's imagine that I'm training a polynomial model with p different powers of x. This p is a parameter which controls the capacity of the model. The larger p is, the larger range of functions our model can represent. We're trying to minimize the loss on the training set using gradient descent, and of course we know that increasing the capacity is going to make it easier to fit our data. So if we let it, the model will choose to maximize p, but then, of course, the model will overfit. And this is exactly why we shouldn't optimize the capacity parameter directly using gradient descent. If we let the model learn it, it's going to learn to overfit that data because that's what gives it the best performance metric it wants. And these kind of variables are the kind of variables which we need to set before training begins. And we call these kind of variables hyperparameters. So other variables are hyperparameters because they actually can't be optimized directly during training. And that's most commonly because they are required before training begins. So some examples might include the choice of the optimization algorithm, the batch size, the learning rate. Essentially, any variable required before training begins or which shouldn't be learned by the model is a hyperparameter, and we should set those before training. And tuning hyperparameters is the main reason that we need the validation set. Evaluating them on the training set won't tell us how well the model generalizes to unseen examples, and evaluating those hyperparameters on the test set will likely lead us to overfit to perform well on just those examples. And one common mistake is evaluating different hyperparameter combinations on different validation sets by creating new splits every time you go to test a permutation. Each permutation of hyperparameters should be evaluated fairly on the same validation set. And reporting the score for a model is totally useless without hyperparameter tuning. You may be reporting a bad score simply because you've got bad hyperparameters set. So never report the score of a model without having undergone hyperparameter tuning first. So how do we find the right hyperparameters? Well, we need to obviously try different hyperparameters out and evaluate their performance on the validation set. But of course, we want to have some kind of strategy to the search instead of just trying what we feel like. So a basic strategy would be random search, where you sample random values within a range for each hyperparameter. And a more exhaustive way to do that would be a grid search, where you try every possible combination of features within a range using the grid. And grid search might be more comprehensive, but random search will explore a wider range of parameters quickly. So it depends on what you're doing. Maybe you've already got an idea of where good parameters lie. You might want to use a grid search. If you really have a wide option and you want to home in on something, you might want to use a random search. And there's many more different, much more complex whole branches of research dedicated to this topic of finding the right hyperparameters. But I'm just going to cover these basic ones here. So of course, we can implement these strategies in code. And let's look up how to do that with sklearn. So let's just search sklearn. Let's go random search. See what comes up. Cool. First thing, sklearn.model selection.randomized search CV. Let's take a look at that and see how it works. So here's where we can find it. Here is all of the different parameters which it takes in. Description of what it's going to do. Sounds like what I'm looking for. I can see then in more detail the different parameters which I need to pass this class. And I'm basically going to try and figure out how to use this in code. So what I usually do is, just take a quick scan of this. Okay, it makes sense. Probably estimate that's just a model. Param distributions, probably, with what distribution am I going to sample from each of the different parameters? Just a quick scan of that. Scroll down, take a look at the example, which is always down here. So I'm going to implement something like that. I've actually already got one prepared. So here's what that looks like in code. So I've imported sklearn, imported a model which I'm going to use. This is a random forest regressor. from the ensemble module of sklearn. And down here, I've loaded in the iris dataset. I've created this model, which I'm not going to talk about the details of. And then I've defined this parameter distributions variable, which I'm going to pass in as the second argument to this sklearn.model_selection.randomized search CV. So this parameter distributions is something that's required. For it there, and best number of estimators found was 8. So similarly, we can also use the grid search, and so do a similar thing here, except instead of passing in the parameter distribution, we just pass in the parameter grid. Now, grid search is going to search all of those options, so every possible combination of these two different hyperparameters are going to be evaluated in the model, and we'll see how they come out. You can also see that the grid search took longer to run because it's checking all the permutations. The n estimators is a capacity controlling hyperparameter. Let me do that bit again. And you can also see that the grid search took longer to run because it's checking all the permutations. The n estimators is a capacity controlling hyperparameter. It controls kind of the range of functions, how complex the functions are, which this model can represent. But you can see here that the model with the best performance doesn't use the largest value. And that's because under the hood, the search is measuring performance using cross-validation on the validation set, not actually evaluating its performance on the training set. The best performance on the training set would probably come from the model with the highest capacity, which would have that highest value for n estimators. But in our case, that's not the best value. It's because this performance, which the best score is being reported on, is not for the training set, it's for the validation set. And that's why, as the CV for cross-validation in the name suggests, the train validation splitting is done inside of these classes. So we should pass in the whole training set rather than just one of those splits. Obviously, once we've removed the test set, that is. And by default, inside these search algorithms, I believe they used k-fold cross-validation with 5 folds. So that means you have to be careful applying this default keyword argument for larger models. Doing k-fold cross-validation on a single model is costly enough. Let me do that again. Doing k-fold cross-validation on a single model is costly enough, let alone doing that for many different hyperparameter settings. For each different hyperparameter setting which you want to evaluate, you're going to have to train a new model. So for large models, the number of hyperparameters which you can evaluate will be bounded by the time that you have available. So if you're testing huge neural networks, you're going to probably run into issues there if they take 3 weeks to train anyway. You probably don't have the luxury of being able to run extensive grid searches over thousands of different hyperparameter combinations. And let alone, there'll be far more options than that even. So there are many more hyperparameter tuning strategies and some more advanced work on automatic hyperparameter tuning, but I'm not going to go into that here. There's really just a basic introduction to how you might go about finding those hyperparameters and really what they are. The key things that you need to take away are that hyperparameters are model parameters that cannot or should not be learned directly. They're different to hyperparameters, which are learned directly, usually using gradient-based optimization. And really emphasize this point of reporting a score on a model is totally useless without hyperparameter tuning. You might be reporting a bad score simply because you've got bad hyperparameters set. So always do hyperparameter tuning. And it's pretty easy to implement some of these basic hyperparameter tuning algorithms using sklearn, as I showed. But for larger models, more hyperparameter tuning can be costly because to evaluate each configuration, you need to train a new model.